Good morning, everybody.
Good morning.
Our project is on small sensors and big impacts, microcantilevers, and their mass sensing applications. I am Raymond Lai.
Who's the girl?
Hi, I'm Rob Jones.
Our graduate mentor is Lily Lee, and our primary investigator is Kimberly Turner. Every day we are subjected to molecules and organisms that we cannot sense. Some of these are harmless, but unfortunately some of these are dangerous. But what if we had a device that could detect these contaminants in small quantities with a great degree of accuracy?
So a device we can use to sense these contaminants in the air around us is a microcantilever sensor. These microcantilevers are tiny silicon beams with lengths that range from 400 to 500 microns. Just to put this into perspective, the average thickness of a human hair is 100 microns. And also, to give these microcantilevers sensing ability, we cover them with a special polymer coating that is tailored to attract specific molecules through a lock and key method. So as modeled in the simplified model, the triangle would fit into the polymer, but something like this square will not fit in. So that way we only attract the molecules that we want.
There are many applications we can utilize this technology. For example, we can place them in hospitals to detect harmful pathogens. They can also detect explosives at a high degree of accuracy, rivaling those of the best trained canines. And best of all, they do not put lives in harmful environments. Our goal is to demonstrate the practicality of the microcantilever and optimize accuracy by using different methods of oscillation.
Okay, so believe it or not, microcantilevers have been around for a while. So being around for a while, they have their own traditional method. So this traditional method is through a vertical oscillation. So to demonstrate to you, I have this ruler. We can think of this ruler as a microcantilever as a mini diving board. So the traditional method, we want to oscillate it so that we get vertical oscillations. That's our drive. So just for an example, this would be a vertical oscillation. This is our traditional method. Now, just like this lever, this ruler will stop vibrating, so will the microcantilever. That's the issue with this traditional method. Now, this traditional method is not so bad if you're in a vacuum, but we're trying to be useful in that. If you look around now, there's air. We're not in a vacuum. So our technique to this strategy is to drive it through its horizontal axis, which we call the parametric resonance. That's how we're going to drive it. So that is the slide on the right. So instead of oscillating vertically like this, our method is to oscillate it horizontally through its vertical axis like this. And what this does is it reduces the effects of dampening caused by air resistance. You can think of the air resistance as if you have a diving board, instead of the diving board bouncing through air, it's trying to bounce through a bunch of bowling balls. It's not going to keep oscillating, it's going to dampen down.
The setup that we use to test and utilize these microcantilevers is we generate a high frequency signal from a function generator, pass it through an amplifier, and then the signal from the amplifier has enough energy to drive a piezoelectric transducer to begin oscillating the microcantilever. Then we utilize a laser Doppler vibrometer in order to send an input signal into the microcantilever, and then we get a return signal, which is then read by the oscilloscope, which we could determine the change frequency.
So now I'm going to talk how we gather our data. And basically what we want is, we want to find and oscillate the microcantilever at its resonant frequency, which is the frequency at which it oscillates the widest. That will allow us to have better signals and better detect mass. So basically what we do is we test, we excite the microcantilever, oscillate it, and we test different frequencies until we find the peak in amplitude, the highest amplitude. Once we find this peak in amplitude, the corresponding frequency, so like right here, and in this case around here, that would be well, in the traditional case, that would be our resonant frequency, and we will use that frequency as a standard from which we'll measure any other changes in frequency.
So here we're introducing a new curve, this yellow curve. What the yellow curve represents is our microcantilever actually detecting the mass that we're trying to detect versus the blue curve, which is just the microcantilever oscillating by itself. So the way we can detect these is a change in frequency. And how do we get that change in frequency? We look at the amplitudes, the highest point in the amplitude, this point right here, and we can follow that down to the frequency. And what matters is the change in frequency. Once we can detect the change in frequency, we can detect the change in mass. And that change in mass is the mass that the chemical that you want to identify. So just to give you guys an example, I'll do it with the shoulder again. I have a magnet. This magnet is the mass that we are trying to detect. So everything has its own resonance frequency. This ruler, if I vibrate it, it'll oscillate. Now watch what happens when I attach this mass to it. It should go slower, in theory, but it doesn't always happen that way. There we go. Did you see that? It vibrates slower. It's not as wild as it was. So that change in frequency allows us to detect this change in mass, this magnet, and we can detect chemicals around you, whatever you want to detect.
We learned that between these two methods, parametric resonance is less affected by air resistance, which results in a higher degree of resolution.
Future predictions. We intend to integrate the piezoelectric transducer into the microcantilever, so that'll eliminate two things out of our setup. It'll eliminate the external transducer, and it'll eliminate the need for a laser Doppler vibrometer. We will also have multiple arrays of these microcantilevers to detect a multitude of chemicals. And the future also indicates that they'll be driven down in cost, more portable, more readily available, and with better polymers, we'll be able to detect better chemicals with a higher degree of accuracy. We would like to thank CNSI, our primary investigator, Kimberly Turner, our coordinator, Maria and Jans, our RAs, Mary Lou Bailey, Jordan Grace, Rachel Fleming, Henry Morse, our presentation artist, Stephanie Meadows, and we would like to thank our mentor, Lily Lee.
Thank you all.
Thank you.